Okay, thank you. So I was told that when I moved to the graph setting, some of you became slightly bewildered. I'll try to unbewilder you. This was just trying to give you a bird's eye view of what I'm going to do now. So now I'll go into some more detail. So here's the problem. That it was a popular puzzle in Hungary in the 70s, maybe before the 70s, but in 77, Lovas and Greenwell wrote a paper about this puzzle. So it's the traffic light puzzle. You have traffic light that's red, yellow, green, and it's controlled by n switches. So there's a function from ryg to the n to ryg to ryg. You have n switches. Each switch has 3 positions, and the positions of the switches, the configuration of the switches determines the color of the traffic light. And you're told that whenever you shift every single switch, so if you change the position of every single switch, the color of the light changes. And the question is, what mechanism explains this? So you all know at least one mechanism that explains this. All you have to do is look at the title of the talk. Yeah, just one switch determines the color, and it can be any permutation from the position of that switch to
Could you state once more
you have a function from 0, 1, 2 to the n to 0, 1, 2, and it has the property that if xi is different from yi for I equals 1 up to n, then f of x is different from f of y. And the claim is show that f really depends on a single coordinate. All f does is looks at a single switch, and it takes a permutation of. And Lovas and Greenwell proved this, and they also showed that in infinite products, if you replace n by aleph 0, then this is false. You can build some example coming from ultrafilters that shows that this isn't true. And so Irit asked me about this question, and her motivation came from complexity issues. And here, 10 years later, I'm still doing research related to the question she introduced me to, and I still don't know to explain the exact connection to complexity. But anyhow, so what we really have here, we're looking at the graph K3. K3 is the triangle. And we're looking at the nth tensor of K3 with itself. So what is there are various notions of graph products, and this is traditionally called the weak product of graphs, but it should be called the tensor product of graphs, and I'll explain in a minute why it should be called this. So the vertices of g to the nth tensor power are just the vertices of g to the nth power. It's just the Cartesian product of n copies of the vertices of g. I don't mean this. I mean without the. You just take the vectors of length n whose coordinates are vertices of g, and x is adjacent to y if xi is adjacent to yi in g for every I. So for example, in this graph, the vertices are, you start with a triangle which has vertices 0, 1, and 2. In the nth product, you have vertices which are trinary vectors of length n. One or two of them adjacent. If in every coordinate they're adjacent in the base graph, being adjacent in the base graph just means being different. So 2 are adjacent if they're different in every coordinate. And now I'm asking you to give me a 3 coloring of that graph. Just color the vertices of the graph that go to that are the inverse image of red with one color, then red, and the inverse image of yellow, yellow, and the inverse image of green, green. And this has to be a proper coloring, that if two vertices are connected by an edge, they're colored in different colors. And then show that the only colorings that you have are cylinders. They're colorings that are induced by a single coordinate. Okay, so I want to say something slightly stronger. I want to say that the max independent set in the nth tensor product of K3 is of size 3 to the n minus 1. So if you have every color class is an independent set. You're not allowed to have two vertices with the same color with an edge in between. So no independent set captures more than a third of the vertices. And if you have equality, then I claim this is if and only if it's a dictatorship. So if you give me a proper 3 coloring, I look at the vertices you colored red. Well, one of the I have 3 independent sets, and none of them can capture more than a third of the vertices. So they all each capture precisely 1/3 of the vertices. And if you look at one of these sets, it's determined by a single coordinate, and that will force the other two to be determined by the same coordinate. Otherwise, they'd be orthogonal.
It doesn't matter. In particular, this is stronger than the previous.
This is stronger than this statement. And stability. So if you have an independent set of size 99% of 1/3, then it's 97% of that set comes from is contained in a maximal independent set. And how do you prove this? I want to say that the proof of this is almost isomorphic to the proof I showed you before lunch for intersecting families. Actually, it comes from, it's really almost isomorphic. So let's see what's happening here. And in the paper in ADFS, we show that if you start with some base graph, it doesn't have to be K3. For example, it can be any complete graph. There are a long list of interesting graphs which fulfill what I'm going to say to you. It should be regular. Later we'll see that it doesn't even have to be regular. But in our paper, first we said it has to be regular. It should be connected. And it shouldn't be bipartite. If any of these conditions fail, then what I'm telling you is just not true. And it should be such that when you run the proof through for n equals 1, you get a tight bound. So I'm going to show you some proof that works for any power of the graph. But so you can start trying to do the proof for n equals 1. And if I were to try this proof for n equals 1, I want to prove that the largest independent set in the triangle is of size at most 1 vertex. And I ran the proof through and I'd get only 0.8 vertices. Then I say this graph isn't nice. But if I do this proof for n equals 1 and I get the correct answer, I get a tight bound, then this will hold for all powers of the graph. You'll get the same bound and it will be tight. Now I'm forgetting about colors. I'm just talking about independent sets. I'm going to show you some method of bounding the size of the largest independent set. If this gives a tight bound for the base graph, and the base graph is connected, regular, and non-bipartite, then in all powers of the graph, the maximal independent set has to be a dictator. Okay, so first thing we have to do, we have to find a nice orthonormal basis. So I'm going to take, starting with the base graph. You remember before I had 2 points, now I have 3 points. I want to have a nice orthonormal basis. And remember, it was quite important in the proof that at some point, one of the functions in my orthonormal basis was the constant 1 function. When was that important? Remember, when I looked at the Fourier coefficients, I had to use that f hat of the empty set was the expectation of the function. So I'm going to, when I expanded the function, I needed the fact that one of the functions in the basis was the constant function. I'm going to use this here also. And this is where we'll see this is this at first it seems I can only do this when the graph is regular. So for K3, I'm going to start with I have 3 vertices, and I'm writing a basis for all functions on this 3-point space. And I'll start with 1, 1, 1. I have the uniform measure, and I'm going to just do some, I want to take some orthonormal basis. So I'll choose a basis, and for example, you can take this basis. If omega is the third root of unity, yeah, okay, no, I don't want to take this basis. I'll take some other basis because I'm going to want something additional from this basis. So 1, 1, 1, u and w. So for now I have a basis, and now I have an independent. I'm trying to run this proof, trying to find the largest independent set in the base graph for n equals 1. So I say let f be is indicator of independent set. And remember, for the intersecting family, I wanted to take x and y. They both have the uniform distribution, but such that if x is in the family, y is not in the family, and vice versa. So here, I'm going to take x in the independent set. And if x is in the independent set, then it means that all of x's neighbor, if wherever x is equal to 1, all the neighbors are equal to 0. So I'll say this in a more analytical way. If the value f indicates an independent set, if the value of x is 1 on a vertex, then f is a 0, 1 function. The average of f on all the neighbors is 0. Okay, for a 0, 1 function, saying that the average on all the neighbors is 0 is just saying it's identically 0 there. So if I look at the average of the expectation of f of x and the average on y neighbors of x of f of y, this should be identically 0. So if I look at its expectation, the expectation of this, it should be 0. But this is just a linear operator. What I'm really writing here, I'm writing f times. Okay, so here I wrote the average of f of y on yeah, but now what I really want to do is take just the normalized adjacency matrix of the graph. F is a function on the vertices. Now I want some linear transformation that takes a function and replaces its value at each point with the average on the neighbors. Let's call that matrix A. A is just the adjacency matrix of the graph divided by the degree. So if for our graph, this will be this matrix. So for the triangle, if you take this matrix and you multiply it from the left by a function on the 3 vertices, it will replace the value of the function with the average of the value on the 2 neighbors. So I want to look at the expectation of f times af, which also you can write as the inner product of f and af, if you take the uniform measure. And now somehow this orthonormal basis should come into play. I want to expand f in terms of this basis. But I have to expand f and I have to expand a of f. Now, what would be nice for me about this basis if I have to look at a of f? What would we like the connection between the vectors in the basis and a? Eigenvectors. Excellent. So now we take u and w and hopefully 1, 1, 1. We want these to be eigenvectors of the adjacency matrix. Okay, so let's start with 1, 1, 1. When is the all one vector an eigenvector of the adjacency matrix.
Like you
When the graph is regular, because it just, in every row you have a 1 for every neighbor of the vertex. So when you multiply it by the all one vector, you're just counting how many neighbors the vertex has. And if you get the same answer for all the vertices, then the constant vector will be an eigenvector. So this works for regular graphs. Now, if you look at the adjacency matrix of the graph, it's a symmetric real matrix. So it has an orthonormal basis of real vectors. There exists a complete orthonormal system of eigenvectors of this matrix. So we take those eigenvectors of the adjacency matrix, we fix the first one to be the all ones vector, and take some arbitrary completion to an orthonormal basis.
I think as you define it, it also works not necessarily for regular. So you took adjacency matrix divided by degrees.
Okay, so it depends how you define the inner product and how you define the expectation. That's an excellent remark. I'll get to it in a few minutes. It's true. If you choose the right interpretation of expectation and inner product, this will work not only for regular graphs. That's an excellent remark. But I'll get to that in a few minutes. So, and if you normalize, you divide by the degree, then you'll get the so we'll have eigenvectors, let's call them chi0, chi1, up to chi n minus 1, if there are n minus 1 vertices. And these are the eigenvectors. And the eigenvalues, so if you normalize this, the leading eigenvector, the largest one will be 1, greater or equal to. And if it's known bipartite, the last one, let's call it chi min, or lambda min, it will be strictly larger than minus 1. And if it's connected, then chi1 will also be strictly smaller than 1. Lambda 1, yeah. So we have this basis. And then you just, so the 0, which is the inner product of f and af, it's the sum. I take the expectation of, I expand f according to the eigenvectors. And when I apply A, everywhere where I had as chi s, now I have as lambda s chi s. And when I take the inner product, all the cross terms cancel, and I get, so if f, I should write what f is. F is sum I equals 0 up to n minus 1, ai chi I, then when I do this, I'm going to get sum ai squared lambda I. And from here, the proof proceeds just like what I did before lunch. I take out the A0. I say, let's say the size of the measure of the largest independent set is alpha. I pull out A0, which has to be equal to alpha squared. And I get this is going to be greater or equal to alpha squared plus alpha minus alpha squared times lambda min. And this gives you some bound on alpha. I think it gives you alpha is smaller or equal to minus lambda min divided by 1 minus lambda min. So this gives you, this is Hoffman's bound. Hoffman's bound on max independent set. And for example, for a triangle, it's tight. You get 1/3. And now just like if when I wanted the, so if this works for G, then just tensorize, and it will work for G to the nth tensor power. So let me try to explain that statement. Remember, before lunch I had a function for the two-point space, and when I wanted the function for the nth power of the two-point space, I just took the nth tensor power. I took all the so I had chi 0 and chi 1, and then when I wanted the functions on the n-dimensional space, I took all possible tensor powers of n of these. So I could take chi 0, tensor chi 0, tensor chi 0, tensor chi 1, tensor chi 1, tensor chi 0. I have n of these, and then I get 2 to the n functions, which is the right number. And there are, if I started with an orthonormal basis for the base space, I'm going to end up with an orthonormal basis for the product space, and the new eigenvalues are just going to be the products of the eigenvalues of the base space. And you see, this whole proof, it hinges on the fact that lambda min has to have the right value. If lambda min has the right value, this is going to be tight. So for example, for the triangle, the eigenvalues that you get are 1, minus 1/2, and minus 1/2. And if you plug in here minus 1/2, you get the correct bound, that it's 1/3. But if I have, so if the eigenvalues for the triangle are 1, minus 1/2, and minus 1/2, what are the eigenvalues for the triangle squared? Anything that I can get by taking products of two of these numbers. So the leading eigenvalue will still be 1, but the smallest one will be take 1 twice and take minus half 1 time. And in the nth power, I'm going to take 1, n minus 1 times, and lambda min once, and that's going to be the smallest possible eigenvalue in the nth power. So whenever this is tight for n equals 1, it's going to be tight in the nth power, and you can prove that the maximal independent sets are no larger than what they are in the base case. And now you want to prove uniqueness and stability. You want to prove that not only is the bound true, that you can't have more than 1/3 of all the vertices, but that if you have 1/3, then it's a dictator, and you have close to 1/3, it's close to a dictator. So all you have to do is look back on what you did, what I did before lunch. So the claim, if I have some function and I expand it in terms of the tensors of the, so there were two claims. One is that if I had a polynomial of degree 1, which was Boolean, it had to depend on a single coordinate. And that's an easy exercise here also. And then there was FKN, which said that if you have a polynomial which takes on only the values 0 and 1, and almost all of the L2 weight of its coefficients is on the linear part, then it's close to a dictatorship. That can transfer to here also, but remember when I said before lunch, to prove FKN, to prove this stability result, you need some hypercontractive inequality or Berry-Yassine. So if you want to do it, in this case, you need the analogous statements here, and the analogous statements are true here. So it takes some effort, but it's once you start on the task, you know you're going to finish it. To prove the analogous statements here, if you want to prove the analogous statements with the optimal constant, then that's a bit harder task, and probably you succeed only if you're Polish. There are all these Oleszkiewicz and Wolf and that give you the optimal hypercontractive estimates in all these cases, but the machinery goes through. Okay, so that was sort of I was trying to convey the.
So just for this independence number is a third. This is only one. Can this be derived from Hoffman?
Yes.
Yes.
Yeah, I said that Hoffman says that the bound is minus lambda min times 1 minus lambda min. And lambda min in the one-dimensional case was 1/2, minus 1/2. You plug it in here, you get 1/3. And as I said, if the lambda min of the nth product is the same lambda min as the one-dimensional, so you get the same bound. So this works in products of various nice graphs where nice was regular, connected, non-bipartite, and the Hoffman bound is tight for them. So if that's true for the base graph, it works in the products, and there all maximal independent sets have to be dictators, and you have stability.
Can I bother you with one more question?
Sure.
So is it conceivable that there is something quantitative, a Hoffman quantitative, something stability, which is derived, which follows from the fact that the lower end of the spectrum is somehow very sparse? So these powers, as you described.
No, so for the stability, you need some spectral gap. You need some gap between lambda min and the next smallest eigenvalue. And that gap is the same in the base and in the power. Because think if I take powers of 1 and minus half. Now, multiply these numbers.
This is something that doesn't have to be a product. Just the fact that they know.
Oh, right.
At the lower end of the spectrum,
that gives you stability, yes. You just go through the proof of Hoffman, which is essentially what I did here, and you say, okay, if you're almost equal, you have to shift some of the way to the next eigenvectors, and if the eigenvalues are separated, then, yeah, so, okay. Yes, question?
And the eigenvector in general doesn't have to be Boolean.
No. I didn't use the fact that the eigenvectors are Boolean. I have a Boolean function. I expand it in terms of the eigenvectors. And then in the next step, the eigenvectors disappear, and all I have is the eigenvalues. And the only question is, what is the minimal eigenvalue, and what's the distance between the minimal eigen... If I know the minimal eigenvalue, I can I get the Hoffman bound, and it's either tight or not tight.
Okay,
and
what I meant is that sometimes the Hoffman bound is incorrect.
Oh, that's, yeah. So for C5, you don't get the...
For an NP-hard independent set instance, that wouldn't be the right answer.
Okay. So, the Hoffman bound isn't always tight. And that's what makes our life much more interesting. So for C5, for example, the largest independent set is size 2, and Hoffman doesn't give that. It gives something that has to do with root 5, but it's... I don't know. The answer is...
C5 is done by theta.
No, but in C5, you're looking at, if you're talking about the Shannon capacity, you're looking at a different product. You have two are adjacent if they're neighbors or the same. So it's like taking this product if you put a loop on every vertex and...
You want to see if something tensorizes, and kind of doesn't always tensorize. Like you have some SVT solution to this single shot game graph. You want to see what happens to the graph power using this solution, single dimensional solution. So here you use an eigenvector. You can imagine using semi-definite programs for this. But then you need to see if something tensorizes, which who knows.
Yeah.
Doesn't always tensorize.
Right. Okay, so that was ADFS. Now let me just alone dinu myself and Sudakov. So now let's take another look at 0, 1, 2 to the n. I was going to say something about the the fact that the graph is regular. So I'll say that I won't go very deep into this. I'll just say that. Okay, let me say something about this. So let's look at this graph, for example. So, and let's call the vertices A, B, C, and D. And I'm not going to do any calculations here about the eigenvalues and the eigenvectors of this graph, But I want to ask, what are the what's the largest independent set in the nth power of this graph? So let's call this graph G. And in this graph, you have an independent set that has size about 2. Or, yeah, I mean, has size 2. No, I was talking about this graph, but already thinking about the power where you're going to have an independent set of size approximately 1/2. So and now I'm looking at g to the n. So g to the n, the vertices are vectors whose entries are a, b, c, and d. And two vectors are adjacent if they're neighbors in every single coordinate. So here's a very large independent set in the product, which captures about half of the vertices. The vertices of g to the n. I is all vectors u such that at least half of or more than half of the coordinates are B or C. Okay? So if you look at a vector and ask what's the probability that slightly more than half of the coordinates will be either B or C, the probability is about 50%. So about half of the vertices have this property. And if you take two such vectors, they share some coordinate where both of them have B or both of them have C, or one has B and the other has C. And then they aren't neighbors, so that will be an independent set. Now this is clearly as far as you can get from being a dictator. There's no one coordinate which has any more influence than other coordinates on this. So it seems that g to the n has absolutely no structure that can guarantee us a dictator. So then you look at a little bit more closely at this independent set, and for example, you notice that the degree of every vertex here, so the max degree in I is less than square root of 6 to the n. So if you take a vector in this set, so for each coordinate you get to choose neighbors. So for half the coordinates, you have at least half the coordinates have only 2 neighbors, and less than half of the coordinates have 3 neighbors. So you get, if it was precisely half and half, you get 2 to the n over 2 times 3 to the n over 2, which is root 6 to the n. But since you have a bit more 2's than 3's, you get less than square root 6 to the n. This is the maximum degree of a vertex in I. But average degree in g to the n is, well, you do some calculation, it's a half of 5/2 to the n. And 5/2 is larger than square root 6. Right? You know, kids, they have a calculator, so they don't do anything in their heads. So when I'm beside Nati, I never... So 5/2 is greater than 6, because 24 is less than 25, which means that the vertices in this independent set, they touch a very negligible portion of the edges in the graph. So if you don't touch any of the edges in the graph, it's not such a great achievement to be an independent set. I want to see you be in an independent set where you touch a lot of the vertices, okay? Because if you don't touch any of the edges, of course, then nothing of the structure of the graph comes into play. So of course I can't expect any structure. So how are you going to reward a vertex for touching a lot of edges? Just pay it per edge. So paying it per edge, what's the measure on the graph which gives each vertex the weight proportional to its degree? Does this ring a bell? Right, so does it ring a bell? Yes, it's the stationary distribution of the Markov of the random walk on the graph. So this tells you if you choose the and now if you so this tells you that the way you should look at it is look not at the uniform measure on the graph, but if the graph is regular, the uniform measure is the stationary measure of a random walk. But you should start by looking at the stationary measure of a random walk on the graph, and that defines the measure. And now do everything like I said before, and now what I said before is true. If now you do it for the one-dimensional case with this new measure, you can still take an orthonormal basis with respect to this measure. This corresponds to taking a slight change of basis. And if you get the tight bound for the one-dimensional case with this measure, then in the n-dimensional case with its stationary measure, which is the nth product of the stationary measure of the base graph, the theorem will still be true. The maximal independent set will be a dictator, and you'll have stability. By the way, in this example, you don't get a tight bound for the base graph. So I can't guarantee you that this example, the maximal independent sets are. I didn't think about it. I just. Okay, so this morning I was saying, do I have an example of a non-regular graph where the Hoffman bound is tight? I'm sure there are tons of them, but I couldn't come up with one off the top of my head, but I'm sure there are many. Okay, so let's see. So let's concentrate on 0, 1, 2 to the n. So a maximal independent set is take all vectors whose 17th coordinate is 2. Here's an independent set, which is a maximal. Take all u such that at least 2 of u1, u2, and u3 are 0. Okay, so if I have two vectors that at least 2 out of the first 3 coordinates are 0, they share a 0 in some place, so they can't be neighbors in this graph. So this is an independent set. And this has measure slightly less than 1/3. It's 8 over 27 or 7 over 27. You can easily check this later. But this still has some structure. So maybe it's true that this is the only way to get an independent set. Fix a bounded number of coordinates and do something on them. Well, that's obviously false because I can take I, and now I take a random subset of I, just half the vertices in I, and I'll get something. When you just stare at it, it's very hard to see that it has some structure, especially if you look at the Fourier expansion. If I do the Fourier expansion of I, I'm going to see that I get a polynomial that depends only on 3 coordinates. But once I introduce this noise, I take half of the set, I'm going to get a polynomial of degree n, and any Fourier structure that was there is going to disappear. So the question is it true that this is the only way to get an independent set? Take an independent set, take a subset of it. Take an independent set which is a junta, take a subset of the junta, and maybe I allow you to add a little bit of noise outside. And the answer is yes, that's true. So we can write it like this. For every epsilon, so what I'm saying now is true in 0, 1, 2 then, but it's true in all these products where the dependencies in the theorem depend on the base graph. For all epsilon and independent set I, set there exists a a set of vertices J such that, first of all, J depends on J of epsilon coordinates. So there's some function J of epsilon. You tell me you want what dependency you want. I'll tell you the size of the junta. And I'm going to give you a junta that explains your independent set. And what do I mean explains it? I mean that if I look at your independent set and look how much of it sticks out of the junta, the size of this is less than epsilon times the total number of vertices. Okay? So every independent set is explained by a junta. But as I said before lunch, the theorem as I wrote it here is trivial because you can take J epsilon to be 0, take the trivial junta. The whole graph is explained by 0 coordinates, and it contains this completely. So 3 is J is almost independent in the graph G to the J. So J is some, for example, J can be, I just look at the first 3 coordinates, take everything that has at least 2 out of those 3 has 0, and that's some set. You can think of it as a set in 0, 1, 2 to the 3. And that set is an independent set. And here we wanted to say that J is independent and hence completely explains the junta, but we say it's almost independent, which means spans less than epsilon times the number of edges of G to the J. So it's very sparse, but it's not completely independent. Okay, so this is this was the state of the art, or the state of our knowledge until 2 years ago, that if you have an independent set, then we can explain it by a junta, and the explanation is almost complete in the sense that the junta is almost independent. But we conjecture that we can remove this word almost. So we conjecture that the picture is as follows, that in any power of G, if you have, so we conjecture the following, but it's not a conjecture now, it's a theorem. So for every epsilon there exists a delta such that if let's say I is a subset of the vertices of G to the n, and I spans less than epsilon proportion of the edges. So if you have a set which is very sparse, then there exists an independent set J such a J which is a subset of I, such that the size of I minus J is less than delta times the number of vertices in G to the n. Okay, so what does this say? This says that if you have a sparse set that spans few edges, you can remove a small number of vertices and get a truly independent set. Excuse me? There exists an independent set J contained in I such that.
Would it also be true that I has coordinates at least 1 minus delta times J? That would be stronger than if you were.
No, I.
The size of I.
Oh,
The side of I is 1 minus delta, or at least 1 minus delta times.
oh, you're saying that what I have to fix is
If I is random.
no, I is not.
Still, it could be if you.
Maybe J shouldn't be contained in I.
No,
Your question that for any I.
I want to.
no. Okay, no.
The conclusion.
No, but the thing is, if J itself is very small, then the statement holds because I can remove all of J. If J is of constant size, then it doesn't matter if I'm saying I'm removing delta proportion of the vertices or delta proportion of I.
Just the only thing that seems, suggests itself to a change that you're, instead of comparing I and J on the same scale, you compare them on the same
I know, but I'm saying that if I is very small, if I is large, then your question doesn't make a difference. If I is very small, then remove all of I. If I
This,
okay, so,
this would allow you to do this, but the question the way I'm asking it would not allow you to do this.
right. So
Well, we can discuss it later.
okay, so right. No, okay. So I'm sorry. The answer to your question is okay.
Sorry, I should have asked you in the break. Not now.
Again, same J in the two is
Here and here. I mean, your question doesn't make sense in a formal sense. I mean,
yeah, but should I think of it as the same?
yes. Well, you should think of J and J prime. You have J which is almost independent, and then you fix it, and it becomes truly independent.
Try to do the same thing.
You should think of them as J and J prime. That you get J prime. You should think of. This I should be. I should have stated this with calling this I J and this J J prime. Okay. So maybe it wasn't a good choice of notation. So what do I want to say? What do I want to say in the 8 minutes I have remaining? So it's a very hard choice for me. Did I switch epsilon and delta? For every epsilon, right, okay, so for every epsilon greater than 0, there exists delta greater than 0. Yeah. Right, okay, so if you, yeah.
Also switch I and J.
No, I won't. Right, I should have switched them. So, yeah, you specify that you don't allow me to fix more than a very small proportion, a little epsilon, and I say, okay, if your set is sparse enough, has only delta, then I can get away with it. So for every specification that you give me, I can come up with a delta, right? So you're right. So let me say something about Let me say something about the proof of this theorem. So this is with Oded. What?
Started a few minutes after, so you can go a little bit faster.
Okay, yeah, I won't talk for more than 10 minutes. Okay, so the situation is that we have a sparse set, let's say in 0, 1, 2 to the n, and I want to clean it up and have an independent set. And the way we came across the proof is that we realized that this is like the triangle removal lemma. Triangle removal lemma says that in a graph, if you have few triangles, then you can remove few edges and be left with no triangles at all. And the proof of that used Semirady's regularity lemma, the original proof of that, which we couldn't mimic here. This graph is highly non-regularizable. It doesn't, you can't regularize it. But then there came along a new proof of the triangle removal lemma by Jacob Fox. And Jacob, his proof made a big splash because he greatly improved the dependency between the epsilon and the delta in the triangle removal lemma. And so what we basically do is we mimic Jacob Fox's proof of the triangle removal lemma. So we have two proofs, one which really follows Jacob's proof, and so you can ask how small can you make delta as a function of epsilon. So if we follow Jacob's recipe carefully, we can make delta 1 over delta be a tower of height log 1 over epsilon. So 2 to the 2 to the 2 to the 2 of height log 1 over epsilon. But there's a very easy proof, an easier proof that I'm going to say a little bit about now, which gives you a tower of height 1 over epsilon, not a tower of height log 1 over epsilon. But here, in what I'm going to show you, I don't define any potential function. I don't know how many of you are familiar with Jacob's proof, but his proof is similar to the proof of the Semirady regularity lemma. He defines some potential function, and every time you iterate, it increases, and it's bounded. It can't increase indefinitely, so that gives you a bound on how many times you can do it. So here's what we do. So let's say you have this set that spans few edges. So by using the previous theorem I mentioned, DFR, you know that you can more or less, the set is more or less contained in some junta. So here's your set. The junta, if it depends, let's say, on 10 coordinates, then I should have drawn 3 to the 10 blobs here. This is what the junta looks like. And most of my set is captured in, is explained by these, I don't know, out of the 3 to the 10 blobs defined by these 10 coordinates, I take some of them, and almost all my set is contained in the blobs that the junta likes. And maybe there are some blobs that have very little in them. And but the problem that we set out to fix was that some of these, now I look at the graph 0, 1, 2 to the nth, to the 10th, assuming my junta has 10 coordinates, some of these blobs have edges between them. So what we're going to do is say, I know there are edges in here, but there are very, very, very few edges, because my set, I'm going to make delta very, 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 very small. And therefore, this is very sparse. So there are very few edges in here. And now, in DFR, we said if a set is independent, you can explain it, but it's captured by some junta. But it also says if the set is very sparse, it's explained by some junta. So if you look through the proof, you get that every time you have some situation that you have very, very few edges here, there's some explanation for it. So I was only looking at 10 coordinates, but actually the reason there are very few edges here is there's some 11th coordinate or 11th, 12th, and 13th coordinate that because, so let's say 99% of these vectors chose the 11th coordinate to be 0, so they won't have any edges between them, so this is going to be very sparse. So what DFR tells us that if I add another coordinate, so if I cut these potatoes into parts, I'm going to get that my set is explained by this new cut, that what it's going to look like is that most of, let's say if I added the 11th coordinate, almost all of my set is going to sit in where the 11th coordinate is 0 here and where the 11th coordinate is 0 here. So what I'm going to get is that when I cut it into smaller potatoes, some of these potatoes are going to be almost empty, and some of them, the density is going to go up. So now this starts me rolling. Every time I see some edges, I add some more coordinates, and I get a new partition. And the property of this new partition, when I compare it to the older partition, is that in some of the parts the density goes up, and some of the parts of the density goes down. And whenever the density is low enough, I say, I don't care about this part anymore. I'll throw it out. And it's not so hard to see that after some time, I can't continue this anymore. I get to a situation where I have these potatoes where the density is very high, and the set of these potatoes is going to be an independent set, a truly independent set. And I have these potatoes where the density is very low. If I take the union of all of them, that's going to be what I'm going to throw out. And yeah, so that was a very high-level description of the proof, but this is the easy proof. The one that gives the tall tower, actually not much more goes into it than what I said. So the only difficult thing in the proof is that you need this engine. You need some theorem that tells you that when you have two sets that span few edges, the reason for that is that there's some more influential coordinates that you haven't looked at yet. So if you make a finer partition, you're going to get a better picture of what's happening. And then just continue using that theorem over and over, and you'll get a clearer and clearer picture. And at some point, you'll be able to throw away all the fuzzy parts and be left with a truly independent set. Okay, so that's all.